Okay, so welcome to this next video in the theory on probability, and we are going to look at a truly beautiful probability distribution. Well, maybe not a beautiful one, but a very nice, easy one in this video. We're going to look at the multinomial distribution. So, the multinomial distribution, and this is just a generalization of the binomial distribution, and I'll explain why once we've seen what a multinomial distribution is. So, let me give you an example of a problem that is going to require the multinomial distribution to solve it. And again, it's a discrete probability distribution, so these are the nice ones. These are the easy to understand ones. No silly probability density functions. We have nice probability mass functions, which are actual probabilities. So you can ascribe an actual probability to a single outcome. Okay, so this is a problem that we will say requires it. So, let's say we have some, let's say baskets. So here we have some baskets, and we'll label this one basket A. We'll label this one basket B. And we can go on, and let's say we have, a certain number of baskets, and we go on using the alphabet. And let's say we have the number of baskets we have. I don't know what letter of the alphabet this will be. In fact, let's make it, no, we won't make it concrete. We'll make it, we'll say that we have, big N actually we'll say little n baskets is more conventional, but just for concreteness we'll say that we have, just so that we can complete the picture, we'll say that we have 5 baskets. So we have A, B, C, D, and basket E over here. But you could have arbitrarily many baskets, and the multinomial distribution is this generalization. Okay, so in the binomial distribution you would just have 2 baskets, which is why it's the binomial rather than, and this is the multinomial because we've got multiple baskets rather than just 2 baskets. Okay, and now the problem is I have some tennis balls here. Oh, in fact, actually, no, don't call that little n, that would be confusing, that's not conventional. We'll call this little k. I got a little confused there. It doesn't matter, I'm just changing my notation now to make it more conventional. We're going to make this little k baskets. Okay, so now what I have is I have some tennis balls down here, so tennis balls. So I will draw a few little tennis balls. And the number of tennis balls I have in this picture obviously is 8, but for generality we're going to say I have little n tennis balls. And basically you can tell what the problem is going to be. I'm going to throw these tennis balls into these baskets, and I potentially don't like all the baskets as much as each other. I potentially like some of the baskets more than other baskets. So there might be different probabilities that I will throw a tennis ball into a basket. So we need a probability ascribed to each one. So I'll call this up here P1 for the probability that I throw it in the first basket, which I've called basket A. Maybe I should have just labelled these baskets by numbers, yes. Let's get rid of the basket A, basket 2. Let's relabel them basket 1, basket 2, basket 3, basket 4, basket 5, etc., all the way down to basket K, okay? And then we've got P2, P3, P4, P5, and of course there's a condition on this. I have to throw it into 1, so the probability should add up to 1. So P1 is the probability that in any given trial, if I throw this ball, P1 is the probability that I will throw it into basket 1. P2 is the same thing for basket 2, etc. Okay, so we have effectively this P probability vector, as it's called, which we'll say is this P vector, which is the vector P1, P2, P3, and in generality, obviously, we need to go all the way down to PK. Okay? Right. And the probability, the question is this. What's the probability, say, that I end up with, what is the probability, well, firstly, let me draw the probability space. The probability space is going to be all outcomes. Oh dear, what have I done there? That looks bad, but never mind. It's going to be all outcomes of throwing the n balls into these k baskets. So basically, I could throw them in absolutely loads of different ways. I could throw all n into basket 1, so let's draw that as a possibility. So all n go into basket 1, and then there's 0 in every other basket. That's a possibility, so that will be an outcome in here. That has a certain probability, which will be ascribed to it. Similarly, there are other possibilities in here. I could throw, let's say, 2 into basket 1, 3 into basket 2, 2, n minus 5 into basket 3, and then 0 into the other two baskets. And again, that will have a probability. Every single one of these outcomes I'm going to put into this probability space. And obviously what I want to know is I want to know what's the probability of getting a single one of these outcomes. I want you to tell me, I want you to give me a certain combination. Well, basically, you will give me a certain number of balls that you want in each basket, and you'll ask me what is the probability of you getting that. And that's the problem of the multinomial distribution. Okay, so because it's a discrete probability space, there is a finite number of total possibilities. If little k is finite and little n is finite, which by hypothesis they are, there is a finite number of possibilities of what can happen here. So this probability space has a finite number of outcomes in it, and therefore we can view the set of events, this fancy f, the curly f, as just being the power set of omega. So every possible subset in here is an event and is ascribable a probability, and obviously then we have a probability measure. Okay, so what we want to do is we want to make some joint random variables on this probability, our abstract probability space, which are going to make it easier to handle. Basically, I want to algebratize it, is a good way of viewing it. So the first random variable I'm going to set up is I'm going to set up a random variable which we could call x1, which is going to ascribe each outcome. So it's going to map each outcome, so each one of these outcomes in this probability space, it is going to ascribe a real number, which is a whole real number, so it can take on 0, 1, 2, 3, all the way up to n. And the way it's going to work is it's going to ascribe each outcome, each whole outcome. Remember, an outcome is this. This is an outcome. It's you have to tell me in each basket what number of balls are in each basket. That's the outcome of the experiment of throwing these n balls into these k baskets. Basically what it's going to do is it's going to ascribe you a number, and that number is going to be how many tennis balls were in basket 1. So x1 is going to map any outcome onto the number of tennis balls, number of balls in basket 1. Okay. Similarly, we can set up other similar random variables. We can set up x2, x3, x4, x5, x6, doing exactly the same thing, but for the second basket, the third basket, the fourth basket, etc. So I will set up a random variable x2 as well, at 0, 1, 2, 3, all the way up to n, because of course you could get all them balls in a single basket. So all of these are possibilities, in fact, and there will be outcomes in here which are ascribed every single possible value here in this probability space. And x3 is going to ascribe every outcome the number of balls in basket 2, number of balls in basket 2, and etc. You make more, and you go all the way up to xn, and that is going to take on values again, 0, 1, 2, 3, all the way down to n, and xn is going to, oh dear, what have I done there? x2 that should have been. Xn is going to ascribe outcomes the number of balls in basket n. Okay, so now what we can do is we can turn this into a joint probability random variable. So we can ascribe each outcome in here, we can ascribe an entire vector. So we can think of this as making a joint random variable. So we can make the random variable x1, x2, all the way up to xn, which would often be called a vector x bar. And remember, this is different from what we've done previously. We've introduced the concept of joint random variables, but we've always been working with bivariate random variables. We haven't ever done multivariate random variables, where you've had absolutely loads of random variables like this, and we're all putting them together in one great one. We've done it with 2 before, and when you had 2, it seemed a slightly less important to call it a vector than it does now. But of course you could have called it a vector. You could call it a single one a vector if you want. It's not very important to call it a vector, or clever, but you can. So now what we're doing, but now when we've got all n like this. It's just, you know, nice to think of that as a whole vector. Okay, and this is going to ascribe to every single outcome. It's now going to ascribe, how many have we got? N? No, it's going to ascribe, oh dear at me, terrible mistake here. We shouldn't go to xn. Why shouldn't we go to xn? That might not be little n baskets. There's generally, in this problem, going to be more tennis balls than baskets. I have made the mistake of getting confused between the number of baskets and the number of tennis balls. I do apologise. The number of baskets is little k, so what we should have done is gone up to x little k, and x little k should have ascribed to each outcome the number of balls in basket little k. I do apologise for that, and similarly we should have had x1, x2 all the way up to x little k, and this is going to ascribe k tuples of real numbers. So it's going to ascribe to every single outcome up here, it's going to ascribe a vector which is how many balls are in each basket. So this one up here would be ascribed, there are n balls in the first basket, so it would be ascribed the vector n, 0, 0, 0, 0. So it's very intuitive, and remember little k here was 5. Okay, and this one here would be ascribed the vector, we have 2 balls in basket 3, we have 3 balls in basket 2, we have n minus 3 balls in basket 3, and I think I said basket 3 when I was talking about basket 1 there. 0 and 0 in basket 4 and basket 5. Okay, so that is ascribing k tuples, so these k real numbers in an order, in a certain order, to each one of these outcomes. And what it will do is it will ascribe a unique k tuple to each of these outcomes, because if you know this k tuple, you know exactly how many balls go into each basket. So each one of these possible outcomes will have a unique one of these, because each one of these will have a unique one of these. So it's in perfect bijection here. And basically, what we now want to do, what we can now view this as, is a problem in a problem in the real numbers. We can ascribe, if we were working with 2 or 3 possibilities, of course we could visualize these vectors in 3 dimensions. Obviously, visualizing a 5-dimensional vector or a k-dimensional vector, where k is greater than 3, is more difficult. But indeed, if you were in 3 dimensions, we can visualize it directly like this, but we can always sort of get some intuition by working with the 3-dimensional case and thinking about it as a picture like this. So there are certain possibilities, certain vectors in here that are going to be possibilities. So all the ones, remember each of the axes can vary between 0 and n, and together all of the components of the vector need to add up to n. So we should note that x1 plus x2 plus all of them, xk, is a constant, and that's equal to n, because each one of them equals the number of tennis balls thrown into each specific basket. So if you add all of that up, you're going to get the total number of tennis balls. And basically what you can now consider having is a function from this Rk space, this subset of Rk. This is a subset of Rk. You can consider having a function which is the probability mass function. So you can ask, what is the probability that x1 is equal to, let's say, little x1, x2 is equal to little x2, all the way up to x little n being equal, big X n equaling some little xn, okay? And you can ask, what is that? And you can think of it as being a function from all of these points in Rk onto the interval 0, 1. So it's going to map you onto the interval 0, 1. Okay, and this we will discuss how to work it out. But what this vector is then said to be multinomially distributed. X bar is said to be multinomially distributed with parameter, firstly with n tennis balls. So you throw n tennis balls, that's saying how many trials you have, n, and then you put a little k down here as well, mult k n, and then you have the vector p. So what this tells you is it tells you absolutely all the information. It says x is multinomially distributed, it's a k-dimensional vector, the number of trials is n, and the probability of each of the outcomes, i.e. x1, x2, x3, all the way up to xk, that should have been, not xn, oh dear, I'm sorry about that, xk down there, all of those are given by the probability vector, which we discussed up here, which is the probability that you go into each one of the baskets. Okay, so what we would now like to work out, well, firstly what I just want to discuss is, in 3 dimensions, what sort of range is this going to work over in R3? So let's say for a moment that, that these vectors are 3-dimensional, i.e. we have vectors x1, x2, x3, and each of these components can take on values ranging from 0, 1, 2, all the way up to n, but together they all have to add up to some constant value. So what we can do is, if x1 can take on every single value, it can, but there's a restriction on it, remember. All of them together have to add up to n. So the first possibility is that x1 is equal to n, and x2 and x3 are equal to 0. So let's just label the axes. This is x1, this is x2, this is x3. So the first possibility is that x1 is equal to n. So let's say this is n, and then x2 is obviously equal to 0 because we've got a 0 component in that x2 axis, and again x3 is equal to 0. Now another possibility, similarly, is that x1 and x3 are equal to 0, and x2 is equal to n. So that's over there somewhere. And finally, the other possibility is that x3 is equal to n, and x1 and x2 is equal to 0. Right. So that gives us these sort of points forming this sort of triangle in between. And basically, if you take the plane, which is x1 plus x2 plus x3 is equal to n, that will be the plane suspended between those 3 points. If you imagine extending it, there's that triangle, and the plane will go off like this and continue on everywhere, obviously. But we are not interested in the parts where either any of these x1, x2, x3s are negative. And if you go beyond this triangle, this central triangle here, so this triangle suspended between x1, x2, x3, all of the bits on each of the axes. So this triangle we're interested in here, if you go beyond that, you'll have one of them will become negative, basically. So we are interested in all integer points of that triangle, and those are the points of R3 that this function is acting on, basically. All points in that triangle, suspended between x1, x2, x3, where all 3 components are integers, they will satisfy this equation, and therefore they are possibilities for this. So that's the sort of range, the sort of domain that this probability mass function is working on in R3, and that's just a good intuition to have. Okay, so now finally let's work out the PMF for this probability distribution. So let's actually work out the answer. Now we've phrased it in terms of a nice way so that we've got this algebra to work with. Okay, right. So let us say then that this vector x is multinomial. In fact, actually, let's cut this video short here because it's getting a bit long, and we'll continue this in part 2.